Hello and welcome back to the Cryptopals Guided Tour. My name is Eli, I'll be your guide. In this video, we'll be looking at Challenge 18. This is from early on in Set 3. This challenge tasks us with implementing counter mode, the stream cipher mode for block ciphers. Not the only stream cipher mode for block ciphers, but it is the most common and probably the most reasonable one in practice. We have a string here, base64 encoded. This string decrypts to something approximating English in counter mode, which is an AES block cipher mode. It works with other block ciphers just as well, but AES is the most common one in practice. Although actually, one interesting thing to talk about with this is that there has been some interest, especially in recent years, in standardizing different block ciphers than AES that differ in that they have a larger block size. And the motivation for that we can see when we turn our eyes down here to the format in this set of parameters. Let's go through them one by one and we'll end on the format. First off, we have a key, no surprises there. It is 16 bytes long using our favorite 16-byte phrase. We have a nonce, which is currently hard-coded to 0. Now, of course, nonce is short for, among other things, number used once. And so you would expect this to change with each invocation of the cipher rather than staying fixed at 0. But for illustration purposes, we have it set to a null nonce at the moment. Finally, we have a format here. This uses 64 bits to store the nonce and 64 bits to store a block count. Now we note that the block count is just the byte count divided by 16 because a block is 16 bytes long. So this is a counter that will keep track of what block of the message we are currently looking at. Counter mode is indeed very simple. Instead of encrypting the plain text, counter mode encrypts a running counter along with the nonce, producing a 16-byte block of keystream, which is then XORed against the plain text. For instance, for the first 16 bytes of a message with these parameters, you would get this keystream block. It would be the result of calling AES encryption on an all-null block with the provided key. For the next 16 bytes, we would increment this block, by which we mean we would increment specifically the counter field within it. And so we see that this goes from 0 to 1. And then for the next block, we do the same thing once again. We go from 1 to 2 here. Counter mode does not require padding. This is true. When you run out of plain text, you just stop XORing keystream and stop generating keystream. One thing to note, of course, is that doing things this way leaks the exact length of your plain text, and in many contexts, the length of your plain text is not intended to be public data, so in these settings, you might still consider adding padding, however, it is not required. Decryption is identical to encryption. You generate the same keystream, XOR, and recover the plain text. So our goal here is to decrypt the string at the top of this function. Function, that might be a typo actually, that might be meant to say challenge, but in any case, the string we're talking about is this right here, which is, of course, counter encrypted, and then use your counter function to encrypt and decrypt other things. Selecting other things to encrypt is left as an exercise to the viewer. And we have a little quip at the bottom here, that this is the only block cipher mode that matters in good code. In 2024, I might suggest that GCM has taken this title from counter mode. And GCM, Galois counter mode, is of course a close relative of counter mode, but it differs in a couple of ways, as we will see in a moment. There was some stat from Mozilla that GCM is used in about 90% of TLS traffic, I believe. It's overwhelmingly popular in practice, and most people do rely on GCM for their everyday security. So, in that sense, I think that is the mode that has won out among good code. But to stop quibbling semantics and get to the point here, pointless being made, most modern cryptography relies on counter mode to adapt block ciphers into stream ciphers because most of what we want to encrypt is better described as a stream than a sequence of blocks. Well, that is, I suppose, true. Although the difference in practice tends to be small. For example, you do still handle a sequence of blocks to get a counter keystream. And we have a quip here, which is moderately related to the above comment. The idea basically being that if encryption and decryption are the same operation, then you end up saving on a lot of things. It's easier to implement, easier to review. If you have to fit it into hardware, you need half as much space, roughly speaking. However, one point that I would make is that technically the decrypt transform, I suppose, is the same, but if you want to talk about decryption as an operation, then good crypto systems are going to be using authenticated encryption like GCM, and so their decryption step is going to include the tag validation step, because that needs to be done prior to actually generating the plain text. Again, we're talking about good crypto systems, which means we can assume encrypt then MAC. And so in that sense, you do have this difference of tag generation versus tag validation when you're comparing encrypt to decrypt. And so that would be one difference that you would have. But I guess that technically applies at the API level rather than the transform level. So I will allow these two to have their quip on the technicality there. But before we jump into the challenge, just because I am apparently in a nitpicking mood today, let's move over to a target that actually deserves it. Let's talk about the NIST standard for counter mode, among others. Now, this is not a hard document to find. It's public access. You just Google NIST counter spec, and it's the first hit. Similarly, you can get the GCM spec in the same way. Now, this one, before I say too much about it, let's note it's from 2001. So you need to read it with that understanding. But there's a couple of things that really bug me about this standard, and I thought I would just take a moment to show them to you, because if you're working with cryptography in practice, you're usually working off standards, and so it's nice to know when, where, and how those standards fall short. I'm not going to go into the why here. So what I want to focus on, most of the document is quite good, actually. It's fine. And we define ECB, CBC, cipher feedback, and output feedback. These two modes, I think that's CFB and OFB, are not seen very often in practice, but they are here in the spec, fun fact. And then finally, we define the counter mode. And this specification is pretty reasonable. It's written in NIST speak, so of course there's a lot of unnecessary levels of abstraction. But I actually quite like the illustration we have here. Note that this top half is encryption and this bottom half is decryption, which is why this might look more confusing than it necessarily needs to. But yeah, you notice that the plaintext and ciphertext's positions get swapped and everything else pretty much stays the same between the encryption and decryption transforms here. But what I want to focus on is here in Appendix B, because one thing, I guess as a preliminary, let's observe here. When you run each of these blocks through AES, each of these plaintext blocks is going to be unique, and so each of the resulting ciphertext blocks will be unique as well. And of course, you might get a repetition if this counter overflows, if it fills up with OXFF and then goes back to 0. But the expectation is that the API would catch that and prevent that. And in fact, you should probably be cutting off your encryption operation well before you get to that point, for reasons that we'll talk about in a later video. But if you do everything as expected, you'll be getting unique plaintext blocks, meaning because AES is a bijective function under any given key, you will be getting unique ciphertext blocks as well, which means that they will not be equal, which means, interestingly enough, that we get similar impossible differentials to what we were seeing with CBC mode in a previous challenge. And I'll pop up a little thing in some of the white space on screen to show you the algebra behind how you prove that. So you get impossible differentials when you're doing things right. However, when you're doing things wrong, you get something much worse. If you reuse a nonce between two encryption calls, obviously the counter is going to be the same. And so you end up reusing plaintext blocks and reusing keystream. And then this starts to feel like a set one challenge where you're trying to recover your message from the reused keystream. And in fact, if we peek ahead here, you'll see challenges 19 and 20 are on breaking fixed nonce counter in a couple of ways, and that'll be a lot of fun. So you don't want to use fixed nonce counter, and really you don't want to reuse your nonces at all. And so you would think that there would be some sort of scheme for nonce management specified. Let's see what actually gets specified here. We assert the requirement of uniqueness at the top, and we say that everything breaks if you don't follow that rule. And we give 2 suggestions for how to do it. We take about a page of text here to define the concept of incrementing, which, I suppose is somewhat non-trivial because you need wraparound and because it only applies to potentially a subset of the bits. And then we have 2 ideas for how to choose our initial counter blocks here. There's the first approach, which is seen less often in practice, and which I like to think of as oops all counter. In this, you have not necessarily the entire block given over to the counter, but you have m bits given over to the counter. And the idea is simply to make sure that every single encrypted block gets a unique counter value. You set the initial counter block to an arbitrary string, and then you increment that with each encryption. The idea here, basically, it's laid out explicitly. All of the plaintext messages that are ever encrypted under the given key are concatenated into a single message, conceptually. They can be distinct messages in practice, but what's happening under the hood would be identical to if they were concatenated. Consequently, the total number of plaintext blocks must not exceed 2 to the m, certainly true. In fact, it should probably be less. Procedures should be established to ensure the maintenance of the state of the final counter block of the last encrypted message, and to ensure the proper sequencing of the messages. Now, this is what stops this version of counter from being popular in practice. Suppose you have a multi-threaded web server, and it has an endpoint that uses a key to counter encrypt. Now, if you were using this scheme, then all encryptions under that key must be performed sequentially. So the fact that you're multi-threaded gets you nothing, because you're still going to have a global counter, and you're going to be locking and unlocking it. So performance-wise, this has a hard time scaling well. It does not really turn out to be practical in practice. Those problems, of course, get even worse if you have distributed systems where your key is spread across multiple devices. For example, suppose you're doing something with HSMs and they all have a shared key that they agreed on through some cool distributed protocol, and then they're serving requests using that key. If you're using this scheme, then they would need to maintain that shared counter on a separate system that they all talk to, and they would need to have locks and unlocks and all sorts of distributed protocols for that. And if any of them go offline, if they're holding a lock, then suddenly everything's broken. You can imagine all kinds of contexts where this would fail. A second approach, and this is the one that we just looked at, is to assign each message a unique string, and here's where we get to the problematic part, a unique string of b over 2 bits, rounding up if b is odd. In other words, a message nonce, and to incorporate the message nonce into every counter block for the message. The leading b over 2 bits, rounding up if b is odd, the counter block would be the message nonce, and the standard incrementing function would be applied to the remaining m bits to provide an index to the counter blocks for the message. Now, nothing too out of the ordinary so far. This is exactly what we saw over here with, of course, the block length fixed to 128 and the field lengths fixed to 128 over 2, which is 64. The thing is, why would you say b over 2? Why don't you just make this a parameter and provide some bounds on it? I mean, I get that it was 2001, but b over 2 turns out to not be that much for nonces, especially with a 128-bit block cipher. But, I mean, back in 2001, like, I like that that's not the top 8 anymore. Yeah, back in 2001, DES was still floating around. Yeah, let's see where 2001 falls in the chronology. Oh, the same year that AES came out. I suppose those are probably correlated events. But in any case, with a 64-bit block cipher, these would be 32-bit fields, which is completely untenable. But even with a 128-bit block cipher, these are still pretty small, and we'll look at that more formally in a moment here, but I want to get through covering counter before we get to that. So my second complaint with this standard, and let me be clear, I mean, this is a 66-page document, and I'm nitpicking Appendix B, Section 2, so let me be clear about the scale of the criticisms relative to the scale of the document. The rest of it is, fine. But one thing that they really could have done better here, and that we will see what it looks like to do it better in a moment, this last sentence here, a procedure should be established to ensure the uniqueness of the message nonces. I mean, yeah, but what should that look like? Leaving this up to engineers, it's handing them a non-trivial engineering challenge that they are not always going to be able to rise to the occasion for. It is handing them a foot gun, and in practice, we do very often see people shoot themselves in the foot with it. It would have been better to give some recommendations around how this could be done, what this would look like in practice, rather than just saying do it. And if you want to see an example of what that could be, let's look at GCM mode. Now, one fun little thing that's completely irrelevant, but that I get a kick out of, if we reset the zoom on both of these, it's fun to just notice the shifts in typography over the years between 2001 to 2007. But moving on to things that actually matter. We have an entire section in the GCM specification devoted to the uniqueness requirement on IVs and keys. So compare over here, one sentence. Over here, one section. I guess that's 3 pages, 4 pages. And if we look at this, yeah, we see that the scheme for GCM is a little bit less trivial, and we will get to this in a later video. I'm not going to dwell on it too much for now. But yeah, we have a uniqueness requirement. The probability that the authenticated encryption function ever will be invoked with the same IV and the same key on 2 or more distinct sets of input data shall be no greater than 2 to the negative 32. Now this is exactly the sort of thing that you want to have, because this is quite easy to evaluate in practice. And if we scroll down here, yeah, you want fresh keys, that much. I was about to say that should go without saying, but in a NIST standard, nothing goes without saying. But IV constructions here, there's 2 ways to do this. There's the deterministic construction, which we will have a lot more to say about in a future video. I'm holding that one off, I think, for set 8. If we go to set 8 here, there's a, yes, key recovery attacks on GCM with repeated nonces. This is a classic attack on GCM that is super good to know about, and one of the countermeasures to it is deterministic IVs. And if you're wondering, nonce and IV are basically used as interchangeable terms here. There's a semantic difference in that the nonce is traditionally considered to be a number, whereas an IV is a bit string or byte string. In practice, that difference is not significant as long as you're consistent about the byte order encoding for your integers. So we have the deterministic construction. We'll gloss over that one for now. And then down here, we have the RBG-based construction. Now, this is what you see much more commonly for GCM in practice, and the same practice has shown up with counter as well, and we will compare the two in a moment. Now, this basically is the idea that you can have some kind of domain separator in addition to your random field. People don't tend to use that, but the random field is what we're focusing on here. The random field shall be at least 96 bits long. Now compare that to 64 bits for the nonce field. That might not sound like a lot, but just you wait. Now, mindful of the constraint that we've specified up here, we are going to place a limit on the number of invocations of the authenticated encryption function in order to keep our probability of nonce collisions at a manageable level. So we say that we can generate no more than 2 to the 32 nonces of 96 bits or more. And there's an acknowledgement here explicitly that this is sufficient to ensure the uniqueness requirement. But how can we determine that? Great question. I'm glad you asked. This is something that I could not believe we had not already talked about on the guided tour. But I searched through all my old videos, and as far as I could tell, I'd never mentioned it. So here it is, the birthday problem. This is a very famous result, and it comes up in cryptography all the time. The famous instantiation of it is the birthday paradox, so-called. In fact, there's nothing paradoxical about it except for the fact that some people find it counterintuitive, which shows that only 23 people are needed for the probability of 2 of them sharing a birthday to exceed 50%. The reason for that is because you have, with any group of n people, a number of independent trials. You need at least one of them to be a success. And the number of trials is simply going to be the number of edges on the complete graph of n vertices. And it should be intuitively clear that as the number of vertices increases, the number of edges will increase exponentially, meaning that you see exponential growth patterns kicking in very quickly here. And so you can reach high thresholds at a surprising speed. And the specific calculations are given here. What we are interested in is not these tables, not any of these interesting identities, but rather in the generalized version, which we will find right here. They helpfully label the heading with collision because they know a lot of people are coming here just to evaluate the probability of collisions. This is what tends to matter in practice. So let's take this and let's implement these functions. This way we can validate that we are meeting our requirements here. We have 2 functions. This first one gives you the probability given n pulls from a distribution of size d. And the second one tells you, given a probability level and a distribution of size d, how many pulls do you need to make to hit that probability level or exceed it? Or I guess they don't specify whether you're exceeding it or not. They're just saying it's approximately equal. But anyway, let's get to it. Just confirming that log is the natural log here, since we need that for the second equation. So now we can get the probability of a collision between 96-bit IVs given 2 to the 32 samples. And we have fallen outside of the range that floating points can support, and so we are just seeing a rounding error. There's an easy way around this. And how do we do this? Let me just remind myself of the API here. I always have to look this up. It's very simple, but there it is. Get context. That should be plenty. And now we need to use actual decimals rather than floating points. Let's see if this works if I just pass some in, or if I'll have to rewrite the function body itself. And there we have it. That's a much more accurate number. 1.16 times 10 to the negative 10 to be precise, which doesn't look all that remarkable in decimal, but if we take the log base 2 of this, there we have it, negative 33. And we note that 2 to the negative 33 is in fact just within the acceptable range here, the acceptable probability. It is 1 notch shy of 2 to the negative 32. So that just barely hits the target. But let's turn this around now, and let's think about the case of counter mode, where instead of a 96-bit nonce, we have a 64-bit one. What would it take, you might ask, to hit that same probability of collision with vanilla counter mode, which you will remember is specified to have a nonce of this size? And then actually, log is going to return a float here, so let's wrap that in decimal. But actually, instead of doing this, I believe decimals have a dot square root. Let me just check if that's actually the case. Yes. Great. Oh no. Oh no. Okay, we're back to where we started. So this, let's see if this works first try. Nope. That was my problem all along, yes, is that I'm just using the log rather than the actual probability. So let's try that again. And I'll clear the screen so that we can start out fresh here. And let's remind ourselves, if we want our counter mode encryption to have the same probability of collision as we deem acceptable for GCM, this is the maximum number of nonces that we can generate before we exceed that probability. And here it is, 65535.99999, which of course you probably already know, but let's just do it. That's 2 to the 16. 2 to the 16 calls to your cipher before you exceed the GCM probability of collision, before you become strictly worse than GCM. So you might have thought I was nitpicking a little bit earlier when I complained about this, but this is what I'm talking about, is like counter mode conceptually is very useful and very influential. In practice, I've seen it used a number of times, and I can think of exactly one time where it wasn't explicitly the wrong choice. So, you know, think about that. All right, but with all that out of the way, let's get to writing some code, because I'm sure you're just as curious as I am to see what this string decrypts to. We will start up our challenge 18 script here. And the first thing we're going to do is bring this in and base64 decode it. Now, one thing I do have to call out here is that in any real API, you will see the nonce handled as bytes rather than as a number. Because when you handle it as bytes, you don't need to worry about endianness, which you can see we have specified here. However, because the problem statement has specified endianness, I'm choosing to write this code using integers, even though otherwise I wouldn't. Now, there's two ways we could write this. We could do everything in one function here, where we generate our keystream, and we XOR it into the plaintext, and it all happens in one big thing here. However, what I think would be more readable, and I'll motivate this a couple ways, but let me say what I'm going to do first. What we want to encrypt is better described as a stream than as a sequence of blocks. This is true. What's even more true is that our keystream is better described as a keystream than as a sequence of blocks. So while the process to generate it might involve a block cipher, let's pretend that we don't even know that, and we just say, okay. And notice, by the way, that the keystream does not depend on the plain text in any way. I mean, this should not be surprising, but it's just an observation I'm making. And so it's nice because we know that the keystream generation will deal with things that are nominally called ciphertext and plain text, even though really they're counters and keystream. We know that there's probably going to be some crowded namespaces here, so splitting these up, putting the keystream into separate functions so that we don't have to worry about this floating plain text variable and we can reuse that name within this function is also going to be nice. So we can generate that keystream. I got to admit, this pop-up is really harsh in my vibes right now. I would love to be able to read my variable names. But what are you going to do? And no, of course, there's one problem here, which is that keystream is not defined. So let's write that. And in fact, let's prefix it with a underscore to indicate that this is meant to be an internal function. So obviously we need AES. And here we have a couple ways of doing this. Count and nonce are both integers, and integers have a 2 bytes, or yeah, 2 bytes right here. A 2 bytes method, which takes a byte order, which can be either little endian or big endian, although it defaults to big. So you could just write 2 bytes plus 2 bytes, and that would work just fine. However, personally, I prefer using struct and struct.pack. And the reason for this is that it doesn't construct intermediate bytes objects. It just gives us one final result, and it allows you to do basically anything you can do with a C struct. You can specify endianness and all this stuff. You see, you've got your ints, your longs, your longs, and we want 64 bits, which is 8 bytes. And I have a vague recollection from the last time that I did this that these results were counterintuitive. So let's just test it out here. Well, I'll be damned. There we go. That actually worked just fine. So we can use that pattern, and we do nonce first, then counter, I believe. Actually, we'll do it like that. And this is our block of keystream. And now what do we do with this? We could have defined a keystream byte string up here and then append these blocks to it. And I'll show you that actually. We'll start with that and then we'll rewrite it. Because this, to me, is the wrong way to do it, but it's probably the more common way. Actually, that should be strictly less than. So something like this will, I believe, work. Oh, no, it won't, because we're doing a while loop. But if we had a termination condition for the number of keystream bytes needed, then we could break out of this, and we could append to this, and then finally take the result and return it. The issue is that that keystream buffer is going to be constantly getting reallocated. It's going to grow with each block we append to it, and you're going to actually see really poor performance as a result of that, because it's constantly needing to allocate new memory at every step. What I would prefer to do is just write this as a generator function, and you can see that that's what I was planning from the start, because I have while true up here. And what this is going to do is it's just going to generate keystream in steps of 16 bytes, and then it's going to yield from each of those blocks, and just keep going forever until you decide that you don't need it anymore. And when the generator function gets deallocated, then it'll stop, obviously. So now we have this, and this, just stylistically, I don't like binding a generator function to a variable, because if you see it written that way, you might assume it's bytes, and obviously it's not bytes, it's something stateful. And so annoying bugs can creep into your code if you treat something stateful as if it's not. So let's just not assign a name to it, but rather just use it directly here. And now that we've written counter encryption, we can remind ourselves that decryption is identical to encryption. And so for that implementation, We can just do this and then we're done. And I'm realizing now that stylistically I probably should have put these in all uppercase because that's how I usually do these things when you have a global constant. So let's just make that change. And now I hope that the suspense is building as we both wait to see if this will work on the first try. And there it is. The plaintext does show up, and it is in fact a very close approximation of English. Reading, "Yo VIP, let's kick it. Ice, ice, baby. Ice, ice, baby." So there you go. That's challenge 18. And stay tuned for some more challenges dealing with counter mode. There's a lot to say about this one. This will be a lot of fun. So I hope you found this helpful, and I'll see you in the next one.